Atomic mass and isotopes. Or, why are the mass numbers on the periodic table not all whole numbers? Well, it has to do with the fact that most elements have different isotopes, meaning they have different numbers of neutrons. An example would be carbon 12 with 6 neutrons, carbon 14 with 8. Of course, to be carbon, they have to have 6 protons. Well, carbon is found in nature as a mixture of these and a couple of other isotopes. So the mass that's listed on the periodic table is the average mass of what we might call a typical carbon atom, which we call the average atomic mass. And if you were to look up on your periodic table, you will see carbon is listed as 12.01. Well, let's look at what we mean by a weighted average. One way is to look at how grades are calculated in this class. You may remember that the weightings are 10% homework, 15% quizzes, 25% tests, 30% labs, and 20% for that exam you'll have in December. If your grades were as listed, they would calculate to an average of 81.8, which would be a B-. However, because you did so well on the labs and that the labs are 30% of the course, if you calculated a weighted average by multiplying the percentage by the grade and adding them up, you'd get 83.8, which means you get a B, and you're probably a little happier. That's what we mean by weighted average. So let's look at a chemical example. Europium is composed primarily of two isotopes. It's 47.8% europium-151 and 52.2% europium-153. And they have masses that are slightly less than the actual number. Well, to determine the average atomic mass of naturally occurring europium, we simply take the mass and multiply it by the percent abundance, and then add those masses together, and we come up with a weighted average of 152.1964, which for the periodic table would be listed as 152.20. And that is how the average atomic mass of naturally occurring europium is determined. Well, we could also go backwards. For example, rubidium is composed of two naturally occurring isotopes and has an average atomic mass of 85.47. It's composed of rubidium-85 and rubidium-87. And so the question is, what is the percent natural abundance of these isotopes in naturally occurring rubidium? Well, it turns out to be an algebra problem, everybody's favorite subject. You see, we know that the sum of the percent abundances times the masses of the individual isotopes has to equal 85.47 AMU. We also know that the percents have to add up to 100. Or if you do the percents as decimal fractions, those decimal fractions have to add up to 1. So if we let x be the percent of rubidium-85, then 1 minus x is the percent of rubidium-87. And as I said, it's an algebra problem. We end up with the 85.47 is going to be equal to 84.912x times 86.909 times 1 minus x. And if you do the algebra, we end up with x being equal to 0.7206. And what that means is then that we have 72.06% rubidium-85 and 27.94% rubidium-87 in naturally occurring rubidium. And those are two of the kinds of problems you will get on average atomic mass.